Hey Macy, I was hiking the other day and it was really foggy. I couldn't see where I was going. After about half an hour, I ended up right back where I started, even though I thought I was heading for that peak over there. It was weird.
Ha! That is weird. I think it's you. I'm sure I'd be able to find my way to the peak blindfolded.
I bet you couldn't.
Betcha I could.
I overheard your argument. It's been reported that people do tend to drift when they can't tell which way is which, like in fog or heavy snowstorms. I wonder if that's really true.
All good science starts with a question of interest. That question is typically developed from some motivating factor. Based on Ben walking in a circle on a hike during a foggy day, the three students determine a research question, which is, despite a person's best attempt to walk toward a destination they can't see, will they tend to drift instead of walking in a straight line towards that destination?
Yes, I just proved it.
Nonsense. You're just weird. A normal person would be able to walk in a straight line.
Let's find out.
After writing a question of interest, the next step is to design a study that allows a researcher to use data from that study to accurately answer the question of interest.
I'm game. We just need to wait for the next foggy day and then we can hike to the peak. You'll see that I get there with no problem.
I don't think we have to wait for the next foggy day. The idea is that a person can't see where they're going. If I blindfolded you, you wouldn't be able to see where you're going, right?
I wouldn't, but Mei Sing would cheat.
We'll assume that no one would cheat. I could blindfold each of you and ask you to walk in a straight line and see if you can do it.
But we could use other senses, like hearing. If I hear cars in my left and you told me to walk down a path next to the road, I could stay on the road just by listening for cars.
You've got a good point. We'll have to do this in a place where there would be no noise or clues that could help you each reach the destination. We'd have to make the conditions just like walking in a forest on a foggy day.
There are several legitimate methods of collecting data. Samples and experiments are the most common. Which method to use is based on the question of interest. In this example, it makes sense to simulate the activity by performing an experiment. One component of a good experiment is to control for other factors that may influence the results. This is done to keep the conditions of the experiment as similar as possible for all participants and to the situation the experiment is trying to simulate.
I've got it. The school football field is way in back, far from the road, parking lot, and other distractions. That might be a good place.
Perfect. Let's do this.
Wait, you are too biased to take part in this. We need students who have no clue what we are trying to prove.
I've got friends I can ask.
Like they wouldn't be biased too?
You're right. The best way is to randomly select some students.
How many?
Well, more than one. We wouldn't be able to learn much from just one student. But if we had, say, 30 students and most or all drifted, we would feel confident about saying that people, in general, tend to drift.
That makes sense. Hey, the boys' PE class is outside near the football field right now. I'll ask them. We can get this done now so that I can prove that I'm right.
Hey, they're all boys. What about some girls?
What's the difference? If the boys drift, I'm sure girls would too.
Maybe, but that's an assumption that we wouldn't be able to prove if we only did this with boys. We should have boys and girls, and probably not all from the current PE class since they are all athletes.
So?
It's the same reason why we should include boys and girls. While it may not matter, it's possible that athletes might be able to walk in a straight line differently than non-athletes. That's probably not the case, but it's best to have a mix. This is why we should randomly select students.
Another key component of a properly designed study is to randomly select participants. This ensures a good mix of subjects, boys and girls, athletes and non-athletes, and so on. This will go a long way to feeling comfortable making a generalization to all students or even all people about the ability to walk in a straight line.
Okay, I get it. The question we're trying to answer is not just about Ben and me. By including a good mix of other people, we can then generalize about other people based on what happens with the experiment, right? But we're only including students in our own school. Isn't that a problem?
Yes, you are right. And we may have to limit the generalization to just students at our school, since it might be hard for us to get a random sample of all people.
So what's next?
First, we need to get approval from Principal Anderson. Then we have to get a list of students. We might even break that list into female athletes, female non-athletes, and male non-athletes.
Who's considered an athlete?
Good question. For now, we'll consider athletes as anyone on a school sports team. Then we'll take a random sample of students from each of those 4 lists.
Do we bring them out to the field at the same time, blindfold them, and tell them all to walk in a straight line?
That would be hilarious. I'll have my camera rolling for that.
No, we'll take one student at a time, line them up under one set of goalposts pointing towards the goalpost at the other end, blindfold them, and tell them to walk towards the opposite set of goalposts.
Okay. It would still be more fun to have them all out there at one time.